Welcome back. This is lecture number 3, video number 3 of the lecture that would have normally been Thursday, April 9th. And it's Black Hole Day. And we're getting there. We have gotten to understanding what escape velocity is. We understand how space-time is curved in the presence of massive objects. We now need to go back and think about neutron stars. Particularly, remember what happens when a neutron star or an object, a massive star, whose remnant is greater than 3 solar masses, collapses. What does that mean? Well, I mentioned at the time, we know of no force that can hold this object up anymore. After neutron degeneracy pressure fails, there's nothing else that can hold this object up. What does that mean? Well, collapses to a singularity. I haven't defined this term yet, but a singularity means an object that is a single point in space. It has 0 radius, 0 size. Its radius is 0. And it has more than 3 solar masses worth of stuff in it. Let's think about that carefully. What is the density of an object whose radius is 0 and has mass as non-zero? It's infinite. Bad things happen in physics and other things when you start dividing by 0. Let's think about the escape velocity. And let's go back to our whiteboard and remember the equation for escape velocity. We just used it in the previous video. Here it is. Escape velocity is 2g times the mass of the object divided by the radius. What happens when we make radius go to 0? What happens to the escape velocity? Go ahead, try to plug this into your calculator. Your calculator can't do it because you can't divide anything by 0. Why not? It's a singularity, it blows up. As radius approaches 0, the escape velocity approaches infinity. The escape velocity from a radius 0 object that has non-zero mass is infinite. Okay, well that's interesting. What does that mean? How does that affect us? Well, that's fine and well and dandy, but infinite velocity we know is not even a possibility. In fact, let's go back and get back to our PowerPoint slideshow. In fact, we know that there's a cosmic speed limit. I've told you this several times. In fact, it comes out of Einstein's theories that nothing can go faster than the speed of light. So really, what is the surface of a black hole? We're interested in the region around which, around this singularity in space, where the escape velocity is equal to the speed of light. Let's try to think about that real quick. We have define a relationship between radius and mass when the escape velocity is equal to the speed of light. All right, let's go back to our whiteboard. We've got our equation here. We know in this case, so let's imagine what we've got here, right? We know, this is our singularity. We know the escape velocity, it's actually a 0 point. I haven't drawn it as 0, you wouldn't be able to see it, is infinite from this thing, but there's probably the further you get away from this thing, the slower the escape velocity is going to be because r gets larger. There is a point around that singularity where the escape velocity is equal to the speed of light. Let's calculate what that radius is. We know at that radius, the escape velocity is equal to the speed of light. See, we can plug that in. At that radius, c squared equals 2gm over r. Let's solve for the radius now. Let's multiply both sides by r. Let's divide both sides by c squared. The c squareds cancel out here. The r's cancel out here. We get r equals 2gm over c squared. Great. I'm going to give this r a little subscript s because we give this radius a name. Specifically, we call it the Schwarzschild radius. I hope I'm spelling this right. I think I am. Schwarz's child radius. after the name of the scientist who sort of came up with this relationship for the first time. So the Schwarzschild radius, again, is no physical thing around this black hole, but it is that radius around which the escape velocity is equal to the speed of light. And since this is sort of a point of no return, you can think of this for this black hole, right? If you were to fall inside of the escape of the event of the Schwarzschild radius, if you get closer than the Schwarzschild radius to that black hole, then you cannot escape because you cannot travel faster than the speed of light, and your escape velocity is now greater than the speed of light. It would take something moving faster than the speed of light to escape this object. And since nothing can move faster than the speed of light, nothing can escape this object once you fall inside the Schwarzschild radius. Okay. Here we were. We've just written it down, the Schwarzschild radius, 2gm over c squared. Black holes are simply objects whose radius is less than their Schwarzschild radius. If you have such an object, light cannot escape. All right, so here is a cool slide that shows light paths exiting some object. Not even light can escape. A photon that is emitted inside the Schwarzschild radius will simply get bent back around. What does that look like? Well, here is what those light divergent paths look like for different objects. For a star undergoing fusion, this is a normal star like the sun. Space-time is warped so little at the surface of the sun that light doesn't even notice it really. It just escapes regularly. White dwarfs are getting small enough and massive enough that it's sort of starting to get the hang of this and sort of feeling the gravity as it escapes. It doesn't prevent it from escaping, but it's certainly feeling it and bending it a little bit as it goes. Neutron stars are pretty darn close to their Schwarzschild limit. And so photons that are emitted from the surface of neutron stars get bent substantially as they leave. It's difficult for them to leave the neutron star. They can, and they do, but it's difficult. Those photons feel a lot of gravity from this neutron star, and that curvature affects them and their light and their travel direction. Here's a black hole. Again, we think this thing might be a singularity at the center, but we don't really know. But the point is, any photon that's emitted from inside this Schwarzschild radius never escapes. They're all bound orbits. This photon will enter kind of like an elliptical orbit around the center of this black hole and will never get out. Anything that falls through the event horizon, the Schwarzschild radius of a black hole within this region, not only can't it escape, it can't even send a signal back to anybody on the outside of the black hole about what it's seeing inside the black hole. Not even light, no signal, in fact. No information can escape from within the Schwarzschild radius of a black hole. That's why they call it a black hole. No light can in fact escape from this area. For that reason, I haven't coined this term. I've used it, but I haven't coined it. We call this the event horizon. Any event that happens inside this radius is unobservable by anybody outside of that radius. And so it's not even true. It might be that this all collapses to a singularity at the center, but even if it doesn't, and there is some other force that we don't know about that holds this thing up, it doesn't really matter because we can never observe that thing. We will never be able to see it. It is permanently hidden from view by the Schwarzschild radius and event horizon, beyond which nobody can get any information from inside of it. Okay, let's do some calculations. What is the Schwarzschild radius of a 10 solar mass black hole? Let's go back to our whiteboard. We know that the radius equals 2gm over c squared. We know that, so we can plug in these numbers. We know what g is, we know what m is, we know what c squared is. We can plug all these things in. You can look up what the mass of the sun is. The mass of the sun let's say the mass of the sun is 2 times 10 to the 30th kilograms. So 10 solar masses, the mass of our star is 10 solar masses. It's 10 times larger than this. 10 times larger, you just add 1 to the exponent. 2 times 10 to the 31 kilograms. That's the mass of our 10 solar mass black hole. What is G? We know that G, 6.67 times 10 to the negative 11 meters cubed per, that's a cubed per kilogram times second squared. We know that C is 3 times 10 to the 8 meters per second. We know that C squared, square the base, double the exponent, is 9 times 10 to the 16 meters squared per second squared. Great. We can just plug all this stuff in and see what happens. We have a 2, we have a 6.67 times 10 to the negative 11 meters cubed per kilogram times second squared. We've got a mass, 2 times 10 to the 30th kilograms, sorry, 31. This is a 10 solar mass black hole. Divide that by C squared, 9 times 10 to the 16 meters squared per second squared. Plug all that in, and you should get a number that is 29,644. What are the units on this thing? Well, let's figure it out. We've got a second squared here and a second squared here. Those go away. We've got a kilogram on top and a kilogram on bottom. Those go away. I've got a meter squared on the bottom and a meters cubed on top. So 2 of them go away. And look, how about that? I've got the unit that I expect to have for distance, which is meters in this particular case. So a 10 solar mass black hole should give us a radius of about, and let's just round this up. This is about 30,000 meters, or about 30 kilometers. 10 solar mass black hole gives us a Schwarzschild radius of 30 kilometers. Okay, now, how does R depend on M? If you double M, what happens to R? It's also going to double, right? So this is a linear relationship between R and M. So this provides us with an opportunity to do this in a slightly easier way. If you have solar masses, I'm going to write this way. R prime equals 3M prime. This is the easy Schwarzschild radius. This is the hard Schwarzschild radius. This one will work for any unit of mass. You just have to convert it to kilograms, right? Everything goes away. You can plug it in. You'll get a number. But if you have, if you have a mass in solar masses, this will give you the radius in kilometers. See how that worked? 10 solar masses gave us 30 kilometers. All you have to do is multiply that number by 10, and you get the radius, the Schwarzschild radius, in kilometers. I put little primes here to indicate that this is a slightly different equation than this one, even though we're talking about exactly the same quantities, right? This 3 has units of kilometers per solar mass, right? I haven't put that in there, but you have to know, if you're going to use this one, you get kilometers on the left and you get solar masses on the right for this mass. It doesn't work anywhere else. If you want to plug in kilograms and get out meters, you have to use this full equation over here. Okay, those are our 2 Schwarzschild equations, Schwarzschild radius equations that we're going to be using. Let's do a quick example. Back to my PowerPoint slideshow. So here's a question. How massive is a black hole whose Schwarzschild radius is 600 kilometers? This is a top-hat question that I would have asked you. You can feel free to do it out, pause the video, see what you get. When you come back, we will solve it together. Okay, welcome back. Let's go back to our whiteboard. And this is certainly one of those equations, one of those problems where we can use the simple formula. R prime equals 3m prime. Now, we're not given m prime, we're given r prime in this particular case. So we need to make sure we solve this for m prime before we go any further. Divide both sides by 3. 3's go away over here. M prime equals r prime over 3. It's the same equation. In this case, we're given r in kilometers. That's okay, because that's what we expect here. We plug in kilometers to this one, and we get out solar masses. That's all we need to do. So in this case, our Schwarzschild radius is 600 kilometers. Again, we don't really worry about units because we know we plug in the right units, we get out the right units. In this case, it's 200. And in this case, we know, since we use this equation, that this is in fact 200 solar masses. Perfect. Okay, that's some calculations that will be useful for this week's homework. We have one more, hopefully, video to do in this particular class session. And that's really going to talk about the weirdness of things in and around the black hole. What happens when you fall into a black hole? What happens to things that are near a black hole? So you're not going to want to miss that. That's sort of the, I don't know, the cherry on the top of Black Hole Day. So stay tuned.